last ITC lunch of the semester. We just heard an excellent ITC colloquium by Chiara Mingarelli, who will speak a little later. We also have our friend and colleague Hans-Walter Rix visiting us from Germany. He will give the Cecilia Payne talk in lecture later today. And speak also at this lunch. So let me introduce the speakers. We will start with Anna Barnacka, who will talk about the Galaxies as high-resolution telescopes, or as we know them, gravitational lenses. And then hear from Hans Walter about a subject that is not necessarily politically correct, but I will read it nevertheless.
I have changed my title in the meantime. I'm my good manners.
Okay, well, I'll read the title.
No. Keep the title. I'm not angry.
It's recorded. So the title I got was Who's Hot and Who Is Not? The distribution of stellar orbits in present-day galaxies, just to make everyone comfortable. The second part is great. And then we'll hear from Chiara, and she will talk about constraining primordial gravitational waves, backgrounds, PTAs, pulsar timing arrays. And finally, we'll hear from our own student, Philip Cowperthwaite, about local cosmology with gravitational waves.
Thank you. Inner regions of active galaxies host the most powerful phenomena in the universe, including relativistic jets, binary supermassive black holes, or even recoiling supermassive black holes. But at scales smaller than a few hundred parsecs, only radio telescopes have angular resolution to resolve those sources. So we assume that majority of emission originate within 1 parsec of the source, and that the radio core traces position of supermassive black hole. I showed you before that we can use gravitational lensing to test this assumption. When there is a galaxy located between us and distant quasar, this galaxy will curve the spacetime. Curved spacetime tells the light how to move. And in such configuration, multiple mirage images of the source are produced. The light, the emission from those multiple images will follow different paths. And those paths will have a different length and also will traverse through different gravitational potential. And this will induce gravitational time delays. And those time delays depend on the position of the source in relation to the lens. So if we can measure those time delays, we can find out from where the emission is coming from. And we can measure the time delays even if we don't resolve the sources. So for example, we can measure time delays at gamma rays because telescopes like Fermi satellite provide excellent resolution. So I will show you an example of using this technique to one of the gravitationally lensed gamma ray blazar, B20218. So we have a well-resolved position of the radio core, and we have also well-measured time delay at gamma rays down to 3 hours. And we can use the lensing to find out whether the radio core and whether the radio emission and gamma ray emission originate from the same place. So we can use well-resolved radio images in combination with a cosmology and the gravitationally induced time delay at gamma rays. And what we find is that the gamma ray flare did not originate from the radio core, and that the distance between the radio core and the origin of the gamma ray flare is more than 6 milliarc seconds. And we learn from that the radio core, because from the radio observations, we know also that there is the radio core, and we know that the jet is pointing in this direction. And we have a gamma ray flare originating from the other side. This tells us that the supermassive black hole must be even further away from the radio core. So this lensing, this example shows us that the radio core is not at the supermassive black hole, and the gamma ray flares are not originating from the radio core as we commonly assumed. But you may think that this is just one example. But this result actually is not in isolation, because recent comparison of the radio positions of the core from VLBI with Gaia observations with the well-resolved with astrometry with well-resolved positions of the quasars show us that there is hundreds of sources for which we have astrometry from Gaia and well-resolved VLBI observations. We have hundreds of sources where we see offsets between radio and optical emission. But Gaia gives us astrometry only for nearby sources and also gives us only the centroid of the emission. And time delays can be measured only for the brightest and the most variable sources. So today I will show you a different idea how we can use only position of the mirage images to find offset between the radio and optical emission. To do that, we will use the caustic of elliptical galaxies. So caustic is a place where mirage images former are created. We can define the caustic as a place, as an envelope of rays that are reflected or refracted by the curved surface or an object. In our case, the curved object is a curved space-time by elliptical galaxy. And when we project those rays into a plane, we get those characteristic shape, diamond shape caustics. So this animation will show us how this lens configuration will work. So the yellow diamond shape is a caustic of elliptical galaxy. Then this green point is the position of the source, and those red points point out position of the mirage images. So when the source is located outside the source, outside this caustic, then we have two mirage images. And now we will change position of the source along the caustic, and we will see how the position of the mirage images are changing. So first, when the source is outside the caustic, we have two mirage images. Then caustic is the place where number of mirage images changes. So when we cross the caustic, we have 4 mirage images. And note that when we get very close to the caustic, even small change in the position of the source produces huge differences in the position of the mirage images. And when we are outside the caustic, again, we have 2 mirage images. So now let's look closer. Let's put few position of the sources close to the caustic and see how position of the mirage images will change. So here you can see that when we put those sources on the caustic, we cannot even resolve the source, those sources. So now we will change the position of the source. You can see those points here. And we will change the position of the source by only half a milliarc second. And we cannot see the change in position of the order of half a milliarc second, but we can see the change in the position of those mirage images. So here's the idea. So when we have a gravitationally lensed source, and the radio and optical emission comes from the same place, then we will observe 4 mirage images at the radio and optical in exactly the same configuration. But if there is even 1 milliarc second offset between radio and optical emission, we will have a different mirage images configuration at radio and optical. And we can use this change, this difference in the position of the mirage images to infer what is the offset between the radio and optical emission. The caustic is a narrow region, so you may wonder, okay, but how often we will have quasars in the caustic configuration? So here is a survey of 20 flat spectrum radio quasars. And now, quick course about how to recognize stars in the caustic configuration. So the caustic is the place where mirage images form and are created. So we have 4 mirage images, and 2 of them just were created. So 2 of them will be very close to each other. So if we look at the first source, we have 4 mirage images, and already the first one is in the caustic configuration. Then the second one have two mirage images. The third one, again, we have 4 mirage images, and 2 of them are very close to each other. So it's, again, caustic configuration. And next one, also caustic configuration. And if you look at the 20 of them, 8 out of 20 of those quasars are in the caustic configuration. So we can use this method to find out whether the optical and radio emission is from the same place or we have complex source structure. But what is more exciting is the future, because soon we will have SKA and Euclid, which will give us hundreds of thousands of gravitationally lensed quasars. And at least 8% of them will be in the Costi configuration. So what Costi configuration gives us? So first, we have a huge magnification as well, because when we are close to the caustic, sources are magnified. Then we have also angular amplification, so we can distinguish whether the sources are from the same place. Also, this gives us a resolution of the order of milliarc seconds, and also it eliminates need of absolute astrometry, because we only need to measure position in relation to each other. And so currently we have 1,000 of sources. In the near future, within like few years, we will have hundreds of thousands of those sources, and it will allow us to identify quasars at a high redshift, because also they will be gravitationally lensed and magnified. So we will be able to find the most distant quasars and study the physical origin of the emission and find out the offset between the emission. And will allow us to find the best sources to follow up with larger facilities like GLWST or ELT. Thank you. Yes.
Then you can have a time dependent.
And also we will have 8 mirage images, so it will be very easy to identify them. Yes, but then also we can measure.
Right. Now, the length scales that you're talking about, milliarc seconds, you were earlier than you. Milliarc seconds, it's still tens of parsecs in the source
Yes.
frame, is it? Or 100, so that's a relatively large. This
Yes.
is from galactic scales. We're not talking about very close to the black hole.
We have also advantage here that we can use relative astrometry. And so we will be able to go even below milliarc second.
But
So,
it's not inside the inner parsec. We're talking about 10 parsecs.
yes, but I think we will find the examples that we will be able to get even better. It will depend on the source, how bright it is, how good a relative astrometry we can do. So 1 milliarc second is easy to get. We can get it now. But if you have better observations, you can go below.
James.
So on the first slide, you show like the Gaia radio offset. And it's like a single radio source and a single optical source, right? Measuring the offset there. And so in principle, that can be caused by like one lobe of a jet kind of being towards you, and the optical source is the AGN. So you're focusing on flat spectrum objects. Does that mean that you're not going to have very many of those contaminants, or do you expect to need multiple images to know for sure that you're seeing the lens as opposed to an offset jet?
Going back to the comparison of Gaia and the VLBI, so those are flat spectral radio quasars, and what Gaia gives us, we don't have like position of the blobs. We only have a centroid of the emission, so we have to kind of guess what that actually it means. Interpretation is that probably you have a large-scale optical emission. So to the second part of your question, like how to identify those sources.
Yeah, well, I just mean like, how do you know it's not just like one lobe of a jet that you're seeing that's offset from the centroid as opposed to a lens?
So, but when you have a lens source, you will see when you have and you have a quasar. So you will see compact emission from the accretion disk, and when you have a jet with blobs, each of them will have separate 4 mirage images. So you will be able to distinguish them if the source is lensed. So each of them will have separate its own images, and you will see when you have a blob, also it has superluminal motion, so you will see also the faster changes in the positions.
Other questions? Erwin?
Do you know the relative coordinate systems used in optical and radio to within a millisecond?
That's the thing. You're asking about astrometry.
Yes.
So Gaia gives us astrometry, so that's why we could
Reference
see.
system. The point is, you do the position in the optical catalog with a reference system.
Yes.
Radio has its own reference.
Yes.
How closely do you know the
For lensing, that's the whole trick. That with lensing, when you have 4 mirage images, with 2 you cannot do that, but with 4 You can. That gives you by its own reference frame, so you don't need to have absolute astrometry at all. That's why this method has this advantage that you have 4 mirage images, so they give you reference frame. So you don't need to have absolute astrometry at all to combine optical and radio emission.
But you measure the optical emission with some telescope.
Yes, in relation, but the only thing you need is a relation of images to each other. You don't need to have absolute astrometry.
How do you get the images with respect to each other?
Mm-hmm.
How do you get the relative positions in the sky?
But this we have.
The same image.
Yes, they are in the same image because the distance
How do you
is.
get the same image when you're looking with radio telescopes and optical telescopes?
Because we have those lenses and we have
So
optical.
you have other things in the image of both that you know is the
Yes,
same.
yes, yes. Yes, so the distance between the images itself is of the order of arc seconds. So we can identify the sources. And then to identify like a smaller changes in relation of optical emission to go deeper, we will use this 4 mirage images frame.
Okay, we need to move.
Well, thank you for the opportunity to give not only my lecture, but also present another result here. I should say I've taken this to be quite informal, and I'm just going to show a few plots. But it is about a paper that just recently appeared, the astute reader may have seen, but that actually I'm very excited about, and that was a rather monumental multi-year effort in dynamical modeling. This is a paper by Ling Zhu and my colleagues in the dynamics group in Heidelberg. Ling Zhu is a postdoc there. And it addresses the question how unordered the motions of stars are in galaxies nowadays. Very broadly speaking, that tells you a lot, allegedly, about the quiescence or violence of the formation history. If gas had the opportunity to settle in a coplanar cold disk, from which then stars formed, and if nothing much happened afterwards, you would expect stars to be in approximately circular orbits, high angular momentum orbits, while in one or two other regimes, either if stars formed at a phase when gas was so abundant that it had no need to settle into a quiescent disk before forming stars, or if subsequently some form of violent relaxation, like a merger, happened, then stars will end up on highly unordered eccentric orbits, and they have no means to regain by dissipation a degree of order. So let me just remind you that in thermodynamics and dynamics, hot and cold are perfectly acceptable terms for the degree of orderedness or not. So obvious bewilderment is a mystery to me. I don't know what was going on in your mind. The other part why I'm excited about this, I have loved and loathed the Hubble sequence. I have loathed it for its qualitativeness, but of course, much of what I just said is encapsulated in the Hubble sequence, and there's an enormous amount of effort doing bulge disk decompositions, which is really a very ad hoc way of doing this. So let me show you what's behind this effort here. This is the modeling of 300 galaxies using so-called Schwarzschild modeling with two-dimensional data of their stellar kinematics. Velocities and dispersion shown up here in the zeroth moment down there from the Khalifa survey. And Martin Schwarzschild taught us to think of galaxies as made up of orbit building blocks. What would the galaxy look like if all stars were on a circular orbit of a certain radius? It would like an annulus. Or if all stars were on very radial orbits. So one should think of galaxies as made up the superposition of orbits. And so then one can go through and say, in order to explain the density distribution, the velocity and the velocity dispersion, what combination of orbits, here just simply characterized by their effective radius, or their semi-major axis, and their circularity. That is the angular momentum normalized by the maximum angular momentum they could have at this binding energy. So 1 is the circular orbit, 0 is an orbit without angular momentum, and minus 1 here. And I should say there's also, if this potential is not axisymmetric, but barred, there are box orbits which also have no net angular momentum, so also fall in here. So what one sees here is that this galaxy, in its inner parts, has lots of low angular momentum orbits. Gray is just the orbit weight. And then throughout has orbits that are nearly on circular orbits and has some other stuff in between. So now this is how you can think of one galaxy in orbit space. Now to represent all 300, which I'm going to show you in the next plot, we just integrated in radius to just see how much does this galaxy, which fraction of stars are on circular orbits, on no angular momentum orbits, etc. So what is shown here is 300 or so galaxies sorted by stellar mass. The Milky Way is about here. So really over the entire range in galaxy masses that contains the vast majority of all stars. Right? The vast majority of all stars live in galaxies somewhere here, actually narrow mass range. So the further back you see, and if you could defocus the plot, it would be even better. What you see is that, let's go to the massive end. The vast majority of stars lives in low angular momentum orbits. Unsurprising, these are the non-rotating ellipticals. That's just a way of looking at this. Actually, at around here, this is the place where you have the most fraction of stars in high angular momentum, nearly circular orbits. It's actually not the littlest ones, because if you're a dwarf galaxy, it doesn't take much to bump you away from a circular orbit. The other thing you see is two other things. At any given mass, there is a vast range of orbit distributions. And the other stuff, and this is indeed, that's the true reason why hot and not is inappropriate, is because it actually turns out the majority of stars are in orbits that are neither. Because indeed, these are orbits that have very distinct angular momentum, but actually, have about half the angular momentum they could have, or about a 2 to 1 or so, or 30% eccentricity. There's also, throughout, occasionally it happens that there are galaxies that have a lot of counter-rotating stars. Remarkably, this galaxy once here gave me a job, but that's a separate story. So the message is galaxies are most disk-like at around a little bit below the Milky Way mass. And also up here, notice that many of these galaxies, they're almost all classified as ellipticals that actually have lots of momentum material, which is my other historical anecdote, which I get to bring up. Because my thesis topic was disks in elliptical galaxies, for which I got an infinity of grief at the time. So I feel redeemed. Now let me look at one little thing. This is a survey that we can actually take volume corrections. But the first thing I want to show is perhaps an obvious thing, is the question of, once you have solved the orbits actually calculated in 3D, you can verify what seems logical. But in dynamics, you could have a configuration where every star is on a circular orbit, but that's perfectly spherical, right? You have orbits like that. No, nature or galaxy formation doesn't choose to do that. The stars that are indeed on high angular momentum orbits form very flat configurations, and then it becomes increasingly more round. The third part I want to show is really, here now we have averaged yet more. we have taken and properly volume corrected, the galaxy population. So you can ask of galaxies of 10 to the 11-ish mass, which fraction of stars is in hot, warm, and cold orbits. And you see that across much of the range that contains most of the stars in the universe, warm is the most common for orbit to be on. And only really at galaxies that have masses of 2 or 3 times 10 to 11, extremely massive, do the hot orbits dominate. And indeed, the only place where disk-dominated galaxies really means very high angular momentum orbit dominated is at around 10 to 10 solar masses. This is really, in Hubble sequence speak, this is where late-type spiral galaxies live. The reason why, and so you can actually go through the literature. Most of these Schwarzschild models are published for 1 or 2 objects at a time, or 5 objects. So actually doing 300 and doing that also for spiral galaxies was a really big effort. What I think, as a takeaway message, there are 2 things I'd like you to take. First of all, the trends, higher mass, bulge dominated or random dominated, holds true. There's a characteristic range where disks dominate most, but the actual normal is a kind of disk-like orbit, namely definite angular momentum, but not very eccentric. I should say this is inside the effective radius because for technical reasons. The other nice thing is galaxy simulators have the hardest time comparing to a Hubble sequence. This is actually, once you have simulations, a plot that you can make very easily and compare whether you got this right, both in the mean trends and in the scatter, period. Thank you. No, I was 2 seconds over.
The simplest model that one can imagine for galaxy formation is one in which you make stars in disks because they are cold.
Mm-hmm.
The rest is mergers.
Mm-hmm.
Can you shed any light on whether this model is ruled out or will be?
Well, I think the arguments that not all stars were born once in a thin disk and only got stirred up by merging are manifold. People who do observations at redshift 1.5 say it is so. Simulations indicate that. There's also reasons that the so-called thick disk was never actually been heated properly. So we don't have immediately age information. So here I would say that a dynamical model here reflects the enforced steady state now. And I think cosmological simulations, to disprove that, I think you would have to try to see whether you can concoct a model, which I don't quite know how, where all stars are born in flat disks and then stir them up. And I don't think that works because you would have to do it by hand, because in cosmological context that doesn't happen.
Is the thick disk warm? Where would the thick disk fall on the y-axis?
Our beloved galactic thick disk.
Yeah.
I think it would fall somewhere here. The other thing is it will depend on which radius, because remember we live outside of the effective radius of our own galaxy. And as I'll show you in a brief plot at 7 minutes past 4, God willing, we live at the outermost tail end of our thick disk. Much of the thick disk is way inside us, and actually our thick disk makes up almost half of the stars in the Milky Way. But I digress.
I was just wondering if you could say something about how degenerate the Schwarzschild model is.
So let me describe in words 2 things to be said about it. The one is what you actually do is you try out all possible potentials. Then in each of these possible potentials, you calculate all possible orbits and compare, right? That's hard to do. This is actually done triaxially and a lot of computation expensive. The one thing we have done is we have actually taken from the NIHAO and from the Auriga project simulated galaxies, made mock data, run them through here, and then actually compared them to that. And it's a non-perfect match, but it actually basically, given that the scatter here, that should be okay.
Naive question, maybe partially asked what you said. Where did this basic information come from?
So the basic information for each galaxy, you have an image, you have a velocity dispersion. Then you assume a potential, you calculate all possible orbits, and you ask which superposition of these orbits matches all of these data. You optimize or marginalize over the potential, then you know the potential, and you get in that potential the orbit distribution that best matches the 0th, 1st, and 2nd moment of the stellar motions. That is, yeah, there are. Say again? That was the technically not unique, but it turns out this already is there's actually also a third integral, right? The up and down motion that has been marginalized out. It is true if we take different subsets, so the photon noise doesn't matter, and if we make mock observations of simulations where we know the truth, it comes out okay. And let me say, it's a lot better than just saying the Jeans equation, because the Jeans equation you can get solutions for which not even an orbit solution exists.
You don't see the dark matter.
No, so this is, it is true that stellar dynamics is an unsolvable problem. If you're not willing to make symmetry assumptions or other things, there's nothing to be learned from stellar dynamics.
Yeah, I want to, can you go a step further? So you seem like in one population here, do you have enough data in the spectrum to actually split it?
So doing this by fitting also the populations is in the pipeline. I have strongly encouraged, no, I don't know the answer. I have strongly encouraged. This question was, you can see this galaxy doesn't have a simple population. Can't you also label each of these orbit weights by an age or by something? And that is a project that my dear colleagues want to do. I told them to not delay the publication of this by another 3 years to solve the next problem. But I will take the message home. And I believe my time is up. The microphone, this is true. Before I run off mumbling, here you go.
Thank you. So great.
Okay, so I'm Chiara Mingarelli, and now for something completely different. I won't be talking about supermassive black hole binaries, but instead about primordial gravitational wave backgrounds and how we can potentially constrain these with pulsar timing arrays, and in fact, with all of the experiments across all of these decades in frequency. So first, I just want to situate us. The gravitational wave spectrum looks like this. At the high frequency end, we have LIGO, which is sensitive to binary neutron star mergers, binary black hole mergers, black hole neutron star mergers, but these are all stellar mass. In the microhertz to millihertz regime, we have LISA, and LISA can potentially detect baby supermassive black holes, 10 to the 5, 10 to the 6 solar masses, and also the white dwarf foreground. Pulsar timing arrays, which I talked about just a few minutes ago, can constrain supermassive black hole binaries. So these are 10 to the 8, 10 to the 9 solar masses. They're the most massive black hole binaries. And at very low frequencies, we have primordial gravitational wave backgrounds. Now you see the primordial backgrounds are listed here and here, but in fact, the primordial background signature should be across all of these different gravitational wave frequencies. So when we talk about gravitational waves, our currency is strain, h. And strain, LIGO usually describes in terms of the change in distance over distance, so a delta L over L. And in pulsar timing, we really talk about the change in time over time. Now, to convert between omega GW, which is the gravitational wave energy density, and the characteristic strain of a background, we use this little formula here. So in order to set your expectation for a flat primordial gravitational wave background, the characteristic strain goes like f to the minus 1, and so h squared goes like f to the minus 2, which then cancels out with that f, and you get a flat primordial background. Also, Lisa's getting its third arm back, which is very nice. So closer to 2034, we'll start including Lisa in a lot more of this work. So just a little cartoon, gravitational waves come in from primordial sources, all sorts of sources. The most important thing to understand for pulsar timing arrays is that the gravitational wave signal changes the proper distance between the Earth and the pulsar. And so the pulsar signals are redshifted or blue shifted. And this is a completely generic result. Earlier in this video, it's two merging supermassive black holes that make the signature, but really any kind of gravitational wave will induce this kind of redshift in the pulsar timing signal. So for primordial gravitational wave backgrounds, this really manifests as a contribution to the present day gravitational wave energy density, or omega GW. And the gravitational wave background spectrum itself is a function of the tensor to scalar ratio and the primordial tensor index NT. So here you have the dependence on NT, and the dependence on R is in here. So when we have new limits on omega GW, this can in turn be mapped onto constraints on R and NT. Now, while we expect NT to be asymptotically equal to 0, there are some non-standard evolutionary models of the universe which can produce blue spectra, or blue NTs which are greater than 0. So these can be, for example, non-inflationary theories like ekpyrosis, where you have bouncing universes, and string gas cosmologies, which Robert Brandenberger really likes to talk about. So the important thing is that we can put limits on these evolutionary theories of the universe and on these cosmologies by looking at limits from not only pulsar timing arrays, but from across all gravitational wave frequencies. So what I want to show you are some results from 2016 in a paper that I wrote with Paul Lasky, Tristan Smith, Tom Giblin, Eric Thrain, and Robert Caldwell, to name a few, and then the rest of the authors are from the Parkes Pulsar Timing Array because we use their data. So this is the first result, and this is supposed to train your intuition. So here we have omega GW, the gravitational wave energy density, and here we have the gravitational wave frequency. Now we have all of these lines. The green line is your standard primordial gravitational wave background that has NT equal to 0, and this is the consistency relation in green. The indirect bounds here are from baryon acoustic oscillations, for example, and the CMB can give you these very low frequency constraints here. Now, these colored lines are the different constraints that you get on NT if you fix the tensor to scalar ratio to be 0.11. So the name of the game here is to hide the signal underneath the detector limit. So for example, if I look at pulsar timing arrays, this black star is the upper limit that we computed for the Parkes pulsar timing array. And so any gravitational wave spectrum that has a blue or greater than 0 index can be hidden underneath that star. So this is the projection for the future, but really this is how we can constrain it. Now, you can see that the gravitational wave experiments that have the highest frequency give you the strongest lever arm on this background. And so here in pink, we have the signal that you could hide underneath advanced LIGO's results. But this is at design sensitivity, not current sensitivity. And that can really limit NT to be less than about 0.68. Now, here we've cheated because we've fixed R and we constrained NT. And I hope that you can understand that we can do better, right? We can take two-dimensional posterior distributions of the results, starting with Planck, and again, to guide your eye, this is the consistency relation in green, and plot what the constraints, the simultaneous constraints are on R and NT. So if we have Planck on its own, you can't really constrain NT very well. However, if you build in BICEP 2, South Pole Telescope polarization information, and then eventually the Parkes pulsar timing array limit, you can see that when you add the pulsar timing limits, that all of this parameter space is ruled out, right? Which is really cool. Because here, you now constrain NT to be about 0.6. And all of this parameter space, which would be well in the realm of ekpyrosis and other more exotic theories of gravity, is ruled out. So now you have this tight cut right here. And of course, it gets even better when you add the LIGO data. So this is all of the gravitational wave experiments combined together. So again here, to remind you, this is what it looks like when you add the pulsar timing data here. And this is in the future when we can add the LIGO and then eventually the Parkes data from 2020. You can again get really strong constraints on NT. And when the tensor to scalar ratio, R, is detected, again, sorry, it's perhaps in bad taste to joke about it. I think it was an important exercise. You can cut through the parameter space and then really constrain the tensor index. The last thing I want to mention are constraints on cosmic strings, which are wonderful things to think about. Cosmic strings decay via gravitational wave emission, and they create a gravitational wave background, again, from 10 to the minus 16 hertz to 10 to the 9 hertz. So really across all gravitational wave frequencies, depending on the loop size. The way that I think about cosmic strings in a very kind of superficial way is a way that was proposed by Wikipedia, so you'll excuse the crude comparison, but I find it effective. They come from phase transitions in the early universe. And so you can think about this like dropping an ice cube in a glass of water and then watching it crack, right? That kind of cracking is similar to what these cosmic strings are. And so these loops, when the strings connect, they can form a loop, and the loop pinches off and emits gravitational waves, creates a background that should be detectable by pulsar timing arrays and also by other experiments. And so in 2015, we put a limit on the cosmic string tension, which was the best limit to date. And so both the amplitude and the slope information from the limits were used to construct these limits here. And for the experts, we used a Nambu-Gatto field theory strings with a reconnection probability equal to 1. And importantly, our upper limits, which are here in red, are 4 times better than the previously published Planck and ACT and SBT pole limits. So here, again, you have the loop scale, and here you have the tension, and our worst limit, right, which is at the very top here in red, would be that G mu is less than 3.3 times 10 to the minus 8. So the EPTA's limit was equal to the Planck limit, and nanogravs was 4 times better. So to summarize, we can constrain the tensor index and the tensor to scalar ratio with a joint observing strategy across all of the gravitational wave experiments. We can rule out exotic theories that have blue spectra, which are greater than 0.36. And current cosmic string tensions are 4 times better than the limit by Planck, ACT, and the South Pole Telescope. So thank you for your attention. I also don't cross the street on a red light.
Also, timing actually has even higher precision.
But the question I had was, so you were talking about very short wavelength gravitational waves that were produced presumably at the end of inflation, because those that were produced early on in inflation were stretched wavelength.
Yeah, so they freeze out at different points. And so that's why there's gravitational waves across the whole spectrum.
Now, the actual horizon of inflation today is about 10 centimeters. Okay, that's often in textbooks, you see that scale. So if you were to, so then it means that when you deal with LIGO detection of wavelengths of order 100 kilometers or whatever, it's still pretty close to the end of inflation. It's just the last few efforts of inflation because the wavelength was not spread by much from 10 centimeters. And so that means that if you are sensitive to the way inflation ends, it's not so much NT during inflation, it's NT at the end of inflation, which is just when the field settles. So one should be a little careful because it may not be a pure power law.
Well, and so we discussed this in the paper, that there could be a running of the tensor index, that this might not be. I mean, of course, this is a very simplistic model, that's pure power law model. And, you're absolutely right that we could have something that's, hidden in the pulsar timing experiment and then takes off and is detectable in one of these bands, or again turns over the other way. There's a lot of different ways of looking at this. And should we expect a power law over 29 decades in frequency? Probably not, right? But this is the first modeling of this, and we're definitely looking at the running of the tensor index.
Questions for Chiara? Yes, go ahead.
Yeah, so has LIGO not made these, put these upper limits yet on, that they've not measured, tried to measure this background? Are there already limits from LIGO?
So they've put limits on the cosmic strings that they were sensitive to in that part of the frequency spectrum. And there was some other work that tried to put limits on NT and R, but one at a time by fixing one and then putting a limit on the other one, but never this kind of the simultaneous fitting. And it's also really difficult to put the limits consistently on the indirect bounds with these other bounds, because these are integrated. These are integrated bounds here, and then these are all at one point. And so Eric Thrain and Joe Romano wrote a paper in 2014 on how to do this in a self-consistent way. And so this is the first time that we applied that kind of self-consistent method.
Ilya Mandel had a paper suggesting that you should maybe build a decihertz detector. Do you think it would help with this particular problem?
So is this the kind of, what is it called? This is like a Big Bang observatory type experiment.
Yeah, I just think it's intermediate frequency between LIGO and timing and these.
Well, maybe not intermediate, but definitely kind of like, so you're saying 10 to the, sorry, what did you say, 10 to the minus 3? Tens of hertz. Yeah, so, I mean, that could definitely be interesting for putting constraints on primordial backgrounds, for sure. Other astrophysical sources there might be a bit weird. I haven't really thought about astrophysical sources that could live there. But that could be an interesting thing to think about.
Or the LIGO sources, they're free and spiral.
Exactly, yeah. So you could have sources that would go through, I mean, we already saw Alberto Susanna's paper about how the LIGO source could have been detected in the Lisa band, and then you would have already been able to do much better sky localization, knowing where it was, and then kind of predicting where it would end up in the LIGO band. So that would just be another kind of data point potentially for that kind of evolution. I also imagine that extreme mass ratios could produce a lot of sources in that band. I think about it a little bit more.
Certainly a lot of things to look forward to in gravitational wave astrophysics.
I completely agree. Thank you. USB-C to VGA? Okay. Thank you. You're welcome.
Where's my, oh, there it is.
Thanks. So I'm Phil Cowperthwaite. I'm a grad student here, and I'm going to talk about something related to gravitational waves, but a little different than what I normally talk about, which is how we do local cosmology with detections with LIGO. So the process of doing this is called the standard siren approach. It's sort of the gravitational wave analog to the standard candle approach used in, say, type 1a supernova for EM cosmology. So the basic idea is that you can obtain a distance to the source entirely from the gravitational wave detection. And this is the luminosity distance, independent of other calibrations such as the distance ladder. So you have a completely independent measurement of the luminosity distance from the gravitational wave detection. You then go out and ideally find an EM counterpart, and that will give you a host galaxy, which is an independent measure of redshift. And then you can use the distance redshift relation to compute H0. So we're too close, so the LIGO probe's distances, they're too small for, say, doing like dark energy and stuff, but it is close enough to do this Hubble constant kind of work. So first, how do we get the distance from gravitational wave detections? There's two parts, basically, where the frequency behavior and frequency chirp, you can think of as giving you the gravitational wave power or luminosity through the detector. And then the actual measured strain with the detector, you can think of as your gravitational wave flux. So once you have a flux and a luminosity, then you can compute a distance. It's actually much more complicated than that, but this is kind of the simplest expression back from the 80s of this idea. So you can see we get this data directly from gravitational wave detection. So for example, this is the frequency behavior of GW 17017, the most recent binary neutron star detection. And then just as an example of a clean plot, this is an example of sort of the strains that we measure with LIGO in the case of GW 170104, which is unrelated binary black hole. More exciting, more interesting for me is the actual finding the EM counterpart. So LIGO sends out localization regions, and we go out and try to cover them. In our case, we use the wide field camera, such as dark energy camera, and you want to try to cover as much of this region and identify a counterpart. So sort of the best case scenario in these searches are you find your counterpart, and there's an obvious host galaxy association. You can get a redshift really easily. Worst case scenario is you don't find anything, of course, and people have made very optimistic arguments that you can do some sort of statistical H0 argument based on the galaxies in the localization volume. So you kind of, what's the most likely host galaxy based on sort of distance and spatial information. So that's the basic idea. We actually had a chance to do this, as I'm sure everyone knows. There's 170817 back in August, which is the first detection of an emerging binary neutron star. So from the gravitational wave data, LIGO determined a distance of about 40 megaparsecs. This was localized to within 30 square degrees, which is great for EM follow-up instead of thousands of square degrees. Had an associated gamma ray burst, which is great. So we have an EM signal. And searches, including those conducted by our dark energy camera team here, found an optical counterpart within 12 hours. It was in this nice host galaxy, NGC 4993, at a redshift of about 0.01. So we have all the information we need to do this, and LIGO, along with these EM follow-up partners, did. So this is the first measurement of H0 from gravitational wave and EM data. So this is the marginalized posterior distribution for H0 from LIGO, shown against Planck and type 1a numbers. There's hope that being an independent measurement, it would help resolve some of this tension, but the peak fell right between the two because nature's cruel. But it's nice because from one measurement, one source alone, we're able to get about a 15% rough measurement of H0. That's really exciting. But there's a couple systematic issues with this. The first is the effect of peculiar velocities in the galaxy on the actual measured Hubble flow. That's not unique to gravitational waves. Everyone has to deal with that, and there's well-established methods for trying to determine that number. More related to gravitational waves are the fact that the distance that you get from that gravitational wave data and the inclination of the binary itself are degenerate, and that's because the gravitational wave signal is stronger along the angular momentum of the binary, so a face-on binary has a stronger signal than an edge-on binary, and you can't break that between just the actual distance to the source. So this is an example of that, the effect of inclination on the actual measured instrument. It's quite banana-shaped. But it's great because EM measurements can help. So we have broadband coverage, and in this picture of the short gamma ray burst, you have this jet that launches, and if you're looking right down the jet, you see an on-axis short jam ray burst and afterglow. But if you're slightly off-axis, then that jet has to take some time to decelerate and slow down, and then eventually we can see it. And by modeling the radio and X-ray data that we take, then you can start to sort of break this distance inclination degeneracy. So this is an example of sort of two models, one for an opening angle of 5 degrees and one for 15 degrees. And you can take this information about the inclination, fold that back into your distance determination, and maybe do a better job of measuring H0. So this paper in 2017 I was on did this. So this is the dashed black line is the original LIGO posterior, and then the green and the blue are posteriors for these different models of either a 5 or 15 degree opening angle prior on the jet. And you can see they do shift it significantly. So the actual effect of the EM observations is important in determining H0. But how are we looking in the future? Because right now this is really just a proof of concept. You do it for one source and you have pretty large error bars. But you really want to get those error bars down and make more precise measurements. So how does this look in the future? So using the rates from this one detection, you can maybe see as many as 1 to 2 mergers per month in the most optimistic case. People have looked at this in the past. You can think for maybe 15 to 20 additional detections. You can get down to less than 10% measurement. That's what's shown here from this Desanthes paper in 2013, where there's lots of individual measurements of H0 from a gravitational wave detection and the actual combined result, which doesn't get you less than 10%. If you want to get less than 1%, these more recent papers suggest you need maybe 40 to 70 detections, with the actual number depending on how well you can constrain the inclination from EM observations. So the ability to do this sort of follow-up is really important in terms of quickly getting a precise H0 measurement in gravitational wave data. And then lastly, sort of prospects for future detections. This is sort of a thing I throw at the end because it's really interesting. So the next generation, decades from now, gravitational wave detectors will be much more sensitive than advanced LIGO even at design. So you can see here, there's this is the advanced LIGO sensitivity curve, and then you have the Einstein telescope and Cosmic Explorer, which are sort of two proposed next generation gravitational wave detectors. There's several orders of magnitude more sensitive. So as a result, we think that you can detect binary neutron star mergers, maybe out to a redshift of 2, maybe black hole binary mergers out to a redshift of 10 to 12, which is insane. But in this case of trying to follow up something like a kilonova at a redshift of 2, then this EM issue becomes very challenging, and we should probably start thinking about how to do that now. So in summary, the first gravitational wave EM event, 1708-17, is showing that we can use gravitational waves to do the standard siren approach and make local measurements of the Hubble constant. It's exciting. People have been talking about doing this for 30 years. From this one event, we're able to get a 15% measurement uncertainty. But if we want to get down to, say, 1% and really start competing with supernova, then you need maybe 40 to 70 such events. But actually constraining the EM counterparts are crucial for driving down these errors. I didn't really get to talk about this, but in the future, maybe we can help inform model constraints on other parameters beyond the Hubble constant, like dark energy or W. And if this is interesting to you, because it's sort of new and exciting, here's some recommended reading on this subject over the past couple of years. Yeah. Right. You have to move to a more complicated expression. Yeah. Yeah, if we can really start to do this at large distances, that becomes very interesting.
Yes. So I was wondering if you could go back to the
of course, sorry.
measurement.
This one or the LIGO one?
The LIGO one.
Sure.
So I don't really have a handle on what the knobs are underneath for making this. I mean, you must have had to constrain a lot of other underlying parameters, and I find it slightly suspicious that the answer from LIGO is right between these two observations. So I was wondering if you could just tell me a little bit about what the dominating knobs are underneath that were turned to get the peak right between the two observations.
I see. Yeah, so really the two dominating systematic effects are the ones I pointed out, which is, how do you go about computing the peculiar velocity error on the actual galaxy itself, and how that's a source of error. And And then once you make assumptions about the inclination or viewing angle from the gravitational wave measurement, those are really the two big things that go into.
So you're telling me that those are the only things?
It's not the only things, but those are. It's mostly. I don't have like a good concrete answer. We can talk about it later, but there's a lot of determining distance and stuff
I
goes
guess I was
into.
just wondering how much can I move this around and still be consistent with the answer? Like how much, like how well constrained is that really?
I see.
Yeah. Anyhow.
Yeah, we can talk about, yeah, no.
We can talk about it later.
Sure.
Just wonder if you could expand a little bit on how the error is expected to improve with the number. You said you got 15% result with 1.
Right.
You said 10% with 15.
That's from many simulated events.
Then you only go up to 70, you get down to 1%. That's the part that seems really
Well, yeah, so it's
very rapid improvements.
yeah, so it can be slightly better than say like root n or something. It entirely depends. It might be many more. It really depends. In that case, that 40 to 70 argument really depends on how well you can model any sort of afterglow jet or any resultant EM emission to place better constraints on the inclination to help.
So it's more than just the number that's more going on in that.
Yeah. It's not just, if I find 50 things, I get such and such error. It depends on how well you can characterize each of those 50 things, because you might get very lucky and get many that are maybe more distant, but maybe you see an on-axis short gamma ray burst, and then you have a much better handle on.
The more you get to, the closer.
Yeah.
You mentioned these are the two main sources of systematic error and how you might get them down.
Mm-hmm.
But what about the other sources of systematic error that you didn't mention? How will those come down with number so that you actually can realize something like you think? Like 40 to 70, getting it down to 1%.
Yeah, that's really more a question for, I think, in other sources are issues in, like, say, the actual processing of the gravitational wave detection, which is not really what I do. So I don't know if I have a good answer for that off the top of my head. But there's been a lot of written about this. So we could, yeah.
So I'm just curious, what is the fraction of the optical counterparts that can be definitively associated with a particular host galaxy? How many do you expect will have energy where it could come galaxy A or galaxy B?
That's a good question. I don't have a number off the top of my head. That's a good question, though. Yeah. So, like, this event was extremely obvious, but I don't think that you should expect that to be the
Why is it that you're
case.
so lucky that the first event was some very distant black hole? It sounds to me like the results are pessimistic.
Perhaps, yeah. It's maybe.
Thank you very much, Philip.
Thanks.
Happy holidays to everyone. See you in February.
Sorry, so it's a very good question, but it's mainly based in gravitational wave data processing, which is not really what I do.
Yeah, no, I kind of understood that. And I didn't
sorry.
want to push too hard because I can't know everything about everything. But I've heard interesting stories about how this particular figure came to be.
Yes.
Calvin, no, it's not yours.
Most colleagues would